With factorials, we have a strategy for counting up the number of ways that you can order a set of objects, but sometimes you might not want to order all of the objects that you have in a set. Sometimes you're going to want to take a subset of the items, but still keep them in some order. And so if we need to count up the number of ways that you can do that, we're going to need to expand out our understanding of the factorial and really work on strategies for trying to count in these situations. So if we're faced with a situation where we have a set of items and we want to take a subset that needs to be ordered ultimately, the number of ways that we can do this is referred to as a permutation. So permutations are going to count the number of orderings of ordered subsets. So how can we motivate this? Using an example, we're going to take 10 books, then we want to place these onto a shelf, but our shelf can actually only hold 5 of the books. And so there's a total set of 10 items. We're going to take out 5 of those items and place them in an order on a shelf. How many possible ways are there of doing this? If we wanted to just take 10 factorial, this is going to tell us that this is the number of orderings of all 10 of these books. And that's not what we're interested in, right? Because we know that the shelf only holds 5 of our books. So how else might we approach this problem? Well, we could turn to the product rule for counting to answer this specific question, right? Because we need to make some decisions. In fact, we need to make 5 decisions. And the first decision that we're going to make is what book goes in the first slot. And when we're standing there off this top, we know that there are 10 total books, right? So you have 10 options for the first slot. But then for the second slot, you're going to have 9 options and then 8 options and so forth. But you're only going to make that 5 times in a row, right? So there are 10 options for our first book, 9 options for the second, third, fourth, and fifth book will have 8, 7, and 6 options respectively. And so the total number of ways that we can do this is going to be 10 times 9 times 8 times 7 times 6, which gives us 30,240. So using just the product rule for counting, we can actually solve this specific example. But what if we want to think about this pattern more generally, right? So what is the general rule here? If we have n distinct items and we want to take a subset of k of them, and we're going to take that subset and place them in an order, right? So we're taking 5 of our books and we're ordering them on a shelf, then the permutations are going to count the total number. In terms of writing down our permutation, we're going to use this notation here where we have this capital P, and then we put a subscript of an n and a k. And so this means that we have a total of n items. We want to take out k of them and put them into an order. P and K is going to count the number of ways that we can do this. And mathematically, the way that we get this is by taking n factorial, so the total number of orderings of all of the items, divide that by n minus k factorial. All right, and so in this case, that is going to give us our total number here, right? Now, what we should note is that if you take the permutations of n and n, this is just going to equal n factorial. And why is this? Well, if you imagine taking this formula here, we plug in an n for k, n minus n is going to give us a 0, right? So then we have 0 factorial in the denominator here, but 0 factorial is defined to be 1, right? And so then if we just take this to be a 1, that crosses out and we're left with just Pnn is equal to n factorial. Okay, and so we can actually get the factorial back directly from our permutations. In other words, if we wanted to take a subset of our items, we have n of them, we're going to take a set of n of them and then order them. That's the same thing as just saying how many ways can we put all n of them in an order. Now with permutations, the critical thing to keep in mind is that the order matters. So we are actually going to be considering the order that they come out in, right? If we have object 1 and then object 2, that's different than object 2 and then object 1. And so whenever we're thinking about permutations, we're thinking about ordering. And whenever we're thinking about ordering, that should prompt us to start thinking about permutations. One way that we can think about doing this as a 2-step process is first we're going to take out the subset, and then we're going to order the subset. And this is going to be a useful way of breaking down sort of more advanced problems. And so if you think about that as sort of the 2-stage process, that's what we're getting with our permutations here. Now, in terms of actually doing this practically, we'll just turn to our permutations formula. But that's a useful way of sort of breaking this down, especially once you're confronted with more complex counting problems. So let's look at some examples here. And for these examples, we're going to want to have a password. And the password is going to be derived without repeating any digits. And what we want to do is count up how many valid passwords there are under certain conditions. So in the first case, we want a 5-digit password using only numeric digits. Okay, and so how might we think about doing this? Well, if we write down what are the numeric digits, right, you can use anywhere between 0 and 9. And so that means there are a total of 10 digits, right? What we want to do is we want to select out 5 of these, right? We're going to choose 5. But of course, because this is a password, the order of your password does matter. So we're going to choose 5, and then we're going to order them. And so then we should be thinking that we want the permutations. There are a total of 10 items. We want 5 of them. And so that's going to be 10 factorial divided by 10 minus 5 factorial, right? And so then we can work out whatever that happens to be. Okay, so we have a 5-digit password using only numeric digits. That's 10 permutations with 10 of size 5, right? And so that gives us 30,240. This is the exact same setting as our book example, right? We had 10 books. We wanted to choose 5 of them. We have 10 digits. We want to choose 5 of them. Okay. Now we want an 8-digit password using only lowercase letters. So again, we think about this. How many total lowercase letters are there? And there are 26 total letters in the alphabet, right? So we have 26 possible things to choose from. We want to pick out 8 of those uniquely and then order those into a password. And so then we're going to have a permutation where the total number is 26 and the size of our subset is 8. And so permutations 26, 8. It's 26 factorial over 26 minus 8 factorial, which gives us the total number there. I will pause here to note that if you're using a calculator to calculate your permutations, you probably have a permutations button. It's going to be shaped like a P. And so if you're not sure how to calculate that using your calculator, I'd advise just turning towards the manual for your calculator or looking it up online because you don't actually need to turn towards your factorial button all the time. It tends to be a little bit quicker just to use the permutations button, but ultimately what it means all mathematically is that 26 factorial divided by 26 minus 8 factorial. You should get the same response no matter what. Now, what if we wanted a 3-digit password using any number or letter, whether that's lowercase or capital? Okay, and so then we need to know, well, how many total possibilities are there of items for us to choose from, right? And what we know is that there are a total of 10 numbers, right? Then we have our 26 lowercase letters and we have our 26 uppercase letters. And so that's going to be a total of 62 items. And so here we need a permutation from a set of size 62 of size 3, right? And that will give us the response that we're looking for. Okay, so we have 26 plus 26 plus 10 is 62 total options, permutations of size 3 from a set of size 62. Turning towards a different set of examples here, we have 12 people who are going to try out for a basketball team. 5 positions need to be filled on a team. So we have our center, our point guard, shooting guard, small forward, and our power forward. And then we want to know how many ways can a center and a point guard be selected. Okay, now importantly, the order matters here, right? If we select person 1 and then person 2, and person 1 is the center and person 2 is the point guard, that's different than saying that person 2 is the center and person 1 is the point guard. And so in this case, because we can distinguish between the different positions, the ordering actually is going to matter. And so what we have is we have a group of 12 people. We want to select out 2 positions. The order matters, and so we need a permutation here, right? 12, 2, which gives us 132 different ways that we can select out the center and the point guard. Now we could also just take this directly using the product rule for counting, right? There are 12 ways that we can select our center. Once we've selected the center, there are 11 individuals remaining that we could use to select our point guard. And so 12 times 11 will give you the same response. And so again, the permutation becomes this shortcut, but really it's resting upon the ideas that we had from our product rule of counting. How many ways can the shooting guard, small forward, and power forward be selected? Okay, and so we can walk through this again. Right? There are 3 positions here, 12 total people to choose those from, permutations 12 from 3, right? Now, supposing that we've selected our point guard and our center already, how many ways are there of selecting the other 3 positions? Okay, and so we've already picked out the first 2 positions, which means that we have 10 people left to choose from. Now we want to choose 3 positions, right? And so there's a total of 10 individuals. We want to choose 3 positions, so the permutations 10 comma 3. Right? And so 10 individuals remaining, 3 positions to choose. P 10 3 gives us 720 ways of doing that. And so there are going to be more ways that we could select the 3 positions if you have all 12 people than if you've already eliminated 2 people, which again should make a little bit of intuitive sense there. Now, how many ways can we select a complete team of 5 with all of the positions assigned? Okay. And so there are actually 2 ways that you could think about approaching this problem here, right? The first way is to recognize that we have 12 individuals. We want to select 5 positions, and so it's a permutation of 12 and 5. And so this is going to give us 95,040. The other thing that you could do, and not that you would have to do this, but it's going to work out in exactly the same way, right, is to recognize that we know there are 132 ways that we can select our center and our point guard. And then, given that we've already selected our center and our point guard, there are an additional 720 ways that we could select the other 3 positions. We've already calculated out those things. And so if you actually do that calculation, you'll find that that gives you the same 95,040 that you have using the permutations directly, right? And so the product rule for counting could still apply here. It's all going to work out in exactly the same way. So, going forward here, how many ways can an alternate team of 5 be selected with positions after we've already selected the starting team? Okay, so you start with 12 individuals. We select out 5 of them. They're our starting roster. Now we want an additional 5 with their positions for our alternate roster. Right, so if you've picked your first 5 out of the 12, there are 7 individuals still remaining. Of those 7 people, we need to pick out which 5 we want, right? So that's a permutation from 7 of size 5, right? So P75 gives us 25 and 20 ways of doing that. So then how many ways can we select the 2 complete rosters with positions, all of those assigned? Again, you could break this down in 2 separate ways, right? The one way that you could do it is using your product rule for counting. The other way is to just recognize that you start with 12 people. We need to select out 10 individuals. All of their ordering matters. And so that's P1210. And that gives us our 239,500,800 total. Okay. If you multiply those 2 numbers that we had before together, you should get exactly the same thing. Now, we want to consider an extension of this. Why is the following argument invalid? Right? So if instead of thinking about what players get put on the teams, what we could instead think about is, well, there are 12 ways to select the first player who's not going to make the team, right? Because if we think about taking a team with 10 individuals total on it, right, then we need to cut 2 people. So there are 12 ways of cutting the first player, and there are 11 ways of cutting the second player, right? That leaves us with just the 10 people we have left. And so then that's going to give us 10 factorial ways of giving them all a position because we can place them into an order there. And so that would tell us that there are going to be 12 times 11 times 10 factorial, which is 479,001,600. And so why does that not give us the same answer? What is the problem with this argument for counting up our totals here? And I'll give you a moment to think about this. Where is that coming from? Why does that not work? Right? Because intuitively, instead of us selecting which people are on the team, we could select which people are not on the team. And then once we have the people who are actually on the team, we can order them. That should work out, right? And so why doesn't it? And the problem that we run into here is that the order does not matter for the 2 people who are cut, right? If you cut person A as your first cut and person B as your second cut, that is the same thing as cutting person B as the first cut and person A as the second cut, right? There is no distinction between those because they're not on the team. They don't get a position. And so, in fact, what we'd be doing here is we'd be essentially double counting all of our situations. And in fact, if you divide this total here, this 479 million divided by 2, you get back to the answer that you actually have here. Right? And so this is showcasing that it's important for us to be really cautious when we start to make these counting arguments, right? Permutations are always going to rely on order mattering. Sometimes order matters, sometimes order doesn't matter. If order doesn't matter, then we have to be really careful to make sure that we're not taking order into account here. Okay. So permutations are going to count our total number of orderings of subsets from a total group. The number of options can be derived using our product rule for counting, right? The permutation rule can actually be derived through that product rule for counting. However, the permutations are going to give us a nice shortcut for this. Critically, the thing to keep in mind is permutations are going to be relevant whenever the order of the subsets actually matters. We have some total number, we want to select out a subset, but then we want to place that subset in order. And if we're dealing with that, we're dealing with permutations, and we can lean on our permutations formula to count up the total ways of doing that.